welcome to the 26th episode of the Water Talks podcast, where water stories, science, and policy receive the focus they deserve. I'm your host, Liss Vanbeckevoort, and today it's my absolute pleasure to welcome Dr. Liss to the show. Stephen is a distinguished water scientist, and he's also the Vice President of Research and Innovation at TMU, and I've had the pleasure of collaborating with him for well over a decade. Welcome, Stephen.
Thank you very much, Alice. Thank you for inviting me to be back here, and look forward to the conversation.
Yeah, I'm excited as well. Stephen was actually our first guest a few years back, but for those listeners that are new, Stephen, can you tell us a little bit about yourself, please?
So as stated in the introduction, I'm the Vice President of Research and Innovation here at TMU and have had a long history in university administration, but I'm also a professor and a microbiologist by background, working as a applied environmental microbiologist at the interface of environmental engineering, environmental biotechnology, and particularly specifically looking at microbial structures in environmental engineered systems, particularly around water, wastewater treatment, understanding those structures and the composition and the factors that influence their formation as they play a very significant role in environmental and engineering processes.
Right.
And that brought us together back in 2007, actually, when I was at the University of Guelph, when you were on shared interest in biofouling and my work in microbial structures and associations through production of extracellular polymeric substances had been a big part of my work and continued to be so both there and then following at Queen's University, where I was a professor of environmental studies and chemical engineering, where we actually begun a lot of work together and established some of the basis of mechanisms of action of stabilized peroxides and how they actually impacted bacteria during microbial controls strategy implementation, where alternative disinfection strategies were being investigated. Anyway, my work spans a lot of wastewater treatment, but I've worked in natural environmental systems, looking at sediment formation, particularly with respect to pathogen, persistent and faded pathogen in receiving waters. And of course, I've turned some attention to water disinfection, water treatment through our collaboration as well.
Exactly. Yeah, no, that's very interesting. And in fact, maybe before we get into some of the more recent work, I remember the first time I saw your license plate on your car, it had Dr. Flock on it. Tell me, what does that mean for our listeners? What's that all about?
Well, not to give anything away about my personal identity, but it's Flock Doc.
Oh, there you go. I got it wrong. Sorry.
I wasn't the first one to have that on my license plate. There was a well-known environmental engineer in California, UC Berkeley, who has since passed on, a legend in his field of microbiology in the earliest days of microbiology and wastewater treatment, who had a license plate with Flock Doc. Anyway, yes. For my 40th birthday, my wife family had purchased vanity plates, Flock Doc. Just around the time we came out with a book on microbial structures in engineered environmental systems, or it was bioflocculation in engineered systems, and we did a lot of work on bioflocculation at the time, and so
yes,
the license plate Flock Doc, and it stuck.
Yeah. No, when I talk to people about you, I say, this man knows about biofilms and knows about how all of these complex structures function. But maybe, wading into our conversation, what are you working on these days? So what's been happening, or what has gotten your attention in water science lately? And maybe that'll build a bridge as we kind of tell a story today for our listeners as we talk about water sustainability and as we talk about some of the practical applications of some of the learning that we've been doing together, and also you with your team there as well.
So I would say outright that sustainability has been probably the single most important element of looking at both conventional and new approaches to water management, wastewater treatment, wastewater management, reducing greenhouse gas emissions, or understanding the basis of the microbial processes that mitigate or contribute to M2O production and wastewater treatment. So sustainability for sure. Around that are new ways of employing some of what we know about different configurations of biological treatment through granular sludge to hybrid type systems. Likewise, on the water treatment side, we're looking at strategies that lead to more sustainable uh, pathways for technology, reducing costs, reducing energy consumption, conserving, minimizing loss of water, and actually really addressing fundamental concerns that are of utmost importance to public health and greenhouse gas emissions in case of wastewater treatment, climate change for sure, and certainly looking at ways in which to improve water quality through its treatment and its distribution, which is a significant part of the transportation of water to the use of water from source to where it is used. And we want to be more purposeful, more intentional, and that also looks to how distributed systems are important and maybe more important in the future of infrastructure renewal and infrastructure replacement, both on the wastewater treatment side and on the water treatment side as well, and empowering those at the consumption side to be more involved in the management of the water and or local and regional management of the water than uh, thinking about highly centralized systems in the context of large municipalities. A lot of the thinking around water, whether you're in small, rural, isolated, and remote communities are concerned, you don't really bring the best of ideas and perspectives that transcend the water, wastewater management and of water. And there's a way of bridging that through looking at more distributed systems, even in the context of a large urban and highly developed populated region. Interestingly enough, I mean, part of the opportunities that present themselves, including capturing digital twins technology in the modeling and design of treatment systems in a way in which you can design and look how to implement and account for all the factors in designing or looking to design and test the optimal properties of the infrastructure for a
Yes.
particular intentional
Yeah.
purpose. So I think a lot of opportunities through digital technology, through sustainability lens, and thinking differently is a very important part of how we need to be thinking about managing environmental resources and managing water, wastewater in particular.
Yeah. No, and I think we'll get into that a little bit further on in our conversation, but it piqued my interest when you talked about, keeping like taking those things into consideration into your design modeling, right? So rather than having some preconceived ideas about, okay, this is how we've always designed a treatment system or a mechanical room and so on and so forth, but looking at the outcomes that you desire at the end of the day, which includes sustainability parameters, key performance indicators in terms of water quality, risk reduction, but also waste reduction. And that can have a significant impact on the front end if you actually know about, those things, or you at least you define them in advance, and then you can use some of those, I think, innovative methods to be able to improve your design from the get-go. But maybe before we get there, distributed water systems, you've mentioned it a couple of times now. For listeners, can you just define that a little bit more clearly or give some examples of what are distributed water systems?
So simply, if you look at just the drinking water environment, it is a distributed system. Just notwithstanding where you might be in a rural farm and you may be drawing water from a well into your system, but there's an aspect of distribution because you pump and then you have to transport that water to the point where you're able to access and use it. To a municipality that treats water at its main treatment plant and then distributes that to whether it's storage tanks
Yes.
or basins and across the region, and from there distributing it through the trunks and the piping systems right to the residences or industries that are using water. And all of that, there's time and distance, and that involves a lot of infrastructure, and it's very specific along that pathway. And so from treatment to distribution, it is a distributed system. And
Exactly.
so, and even within the home, when you think about your cold water supply and then your hot water supply, you divert your cold water or a part of that into a hot water tanks. You may be storing it for periods of time and using it intermittently, and then it's distributed through your house or your residence or within a large building, and that's a distributed system.
Exactly.
That's a very
Okay,
simple
so
way of looking at the distributed system. It's not just, water treatment isn't a system. It's a combination of different components that make up that system.
yeah, and then kind of get to the end user, really, right? So it's kind of, that piece between that to where, the end user would make use of that water.
I'd like to maybe just distinguish that a little bit in the wastewater context. In a large urban setting or even a small community, usually have a centralized wastewater treatment, and the capacity in smaller centers and even larger centers requires not the idea that you just expand and grow the big central facility. That sometimes is prohibitively expensive, and even the repair and
Right.
managing the infrastructure issues is a challenge in those large systems or larger systems. And so
Yes.
if you can imagine, if you needed to add capacity into a smaller community, you might do that in a distributed way, not in the central system, but maybe moving a treatment system to a new subdivision, for example, or moving a treatment system adjacent to a industrial site.
Yes.
And there are many industries that employ wastewater treatment or biological wastewater treatment at site, or at least some form of primary treatment before being discharged into maybe a central system
Right.
down the road.
Yeah, no,
So
that's
yeah, it's a
it's
way
good
of
to
looking at it.
differentiate.
Yeah.
Yeah, no, I understand that, and that's helpful. And kind of trying to build a little bit of framework of our discussion. But I know when you joined us at the first episode, we talked about disinfection, and I think for the purpose of continuing our conversation, maybe could you just explain to our listeners the difference between primary and secondary disinfection and how that relates to a distribution system or a distributed system as well, because I think that's helpful to understand as we look at existing water treatment paradigms and look at sustainability.
Sure. So listen, we've been employing disinfectants and particularly chlorine disinfection for well over a century. And in the first earliest days of minimizing the impacts of contaminated water, this separation of drinking water supplies from wastewater was a very important component of that. So primary disinfection is really the intentional step in reducing the microbial load in the source water that's entering the system. And that is not a sterilization. That is not a complete elimination of all organisms, but it's a reduction in load. And primarily organisms that would be deemed to be pathogens and are attributed to coming from warm-blooded animals, right? Including humans, and that pose risk. And so reducing that microbial load in the first instance ensures that while you're moving that water through the distribution system, minimizing the potential for regrowth and eliminating as many of the pathogens as possible.
Yes.
But then there is a requirement for secondary disinfection that contains growth throughout the distribution system to ensure those organisms that were hit do not grow back, and that should there be other organisms through the distribution system that they don't grow and so forth. But even there, it's not a complete elimination of all organisms. And in all drinking water, there's a natural microflora. Standard disinfection strategies have largely created safe drinking water through management at the primary disinfection and through the distribution system. Or there isn't this disinfection through the distribution system, there is at least at the source a disinfection step.
Right.
So, for example, in a private operated well and distributing it through from the well to the home or to the source where it's used, there may be a secondary disinfectant stage at that point before it is actually consumed or utilized.
Yeah, that makes sense. And I guess then in that way, a distributed system generally, we would be more focusing on secondary disinfection or the protection of that system in general. We could say that.
Yeah, we will talk a little bit about chlorine for sure. This is not about elimination of primary disinfection.
No, absolutely. Absolutely. Yeah, exactly. It's absolutely essential to have that primary disinfection step. But I think it's also good to look at these things, holistically, I guess, and say, all right, we have your primary disinfection. and or you have your secondary disinfection, slightly different purposes and different functionalities. And I think therein lies some of the opportunities that we've discovered in some of our collaboration. And maybe as we think about that in our joint endeavors, we both focus on risk and waste reduction in distributed systems. Like that's a given. Maybe could you speak to your discoveries and how those have an impact on risk and waste reduction in distributed systems? Maybe some of the things that you've learned, maybe high level. I can share some things as well, but how would that kind of, how those two things, how do they intersect with each other?
So, not that we've touched on all options for secondary disinfection and treatment, but I would say the range of tools now available allows various options and perhaps even alternative strategies that are more effective. And so it allows you to be more purposeful and intentional with respect to the design of your secondary treatment system and disinfection strategy to meet the objectives and goals that you need to meet, while minimizing the impacts or some of the negative elements of using one strategy or another, or addressing a strategy that, through a strategy addressing an issue that is not always as easily managed through conventional approaches. And with the advent of new technologies and new methodologies and new tools, it's easy to replace, to add, to transition to new approaches as technology evolves and so forth. The other aspect of this is that many of the new tools are really designed to create more sustainable options and to improve public health and the desire to have water and the quality of water that you would want at the end. And also, if you're looking in an environment such as a controlled growth facility, greenhouses, for example, being able to manage your water supplies and target your control strategies to best support the production and yields and health in those growth facilities, as an example.
Yeah, no, that's a very good example. Maybe stepping back a little bit, like what in your mind encompasses water sustainability in distributed systems? Like what would you be looking at? I know you mentioned at the beginning CO2 emission reductions, obviously the energy required for that water. Like, are there other aspects that you would be looking at as well? Like, what does that encompass?
So first and foremost, it's going to, whatever approach you need to take, it's going to have to meet the requirements that that are in regulation and policy.
Yep.
And have to be performing at or better than the conventional approaches or acceptable tools for which much of the regulation is framed around. So simply, it's got to do its job. So it's disinfection and minimizing regrowth and maintaining residual in the system. For instance, if there isn't something at the end that might be employed, are all important considerations for establishing tools that at least conform to a regulatory framework, but meet the minimum requirements for safety, public health requirements, and so forth.
Yeah. And I think maybe if we look at this in a practical way, then, so yes, it has to be efficacious, it has to be effective, it has to meet regulations. But beyond that, as I've looked at some of the research that we've done in a few different application areas, and I think we could, dive into some of those. The government made it clear only recently. I heard yesterday that, our own food production is going to be a critical focus to becoming more resilient as a country, and being able to provide for the needs of our own nation, besides exports and so on and so forth. So I think agriculture is very important. You've mentioned greenhouses already. They obviously have complex distributed water systems. They recycle all of their water. They have specific growth media that they use to grow the plants in. So what would you say, or how can greenhouses improve resilience in their distributed water systems, considering all of those different complexities and factors that they have? Based on some of the learning that we've done, what would be kind of the message or the practical application of that for a greenhouse, let's say?
A lot in there. So I think one is certainly pathogen control.
Yes.
But that being said, there's also important organisms that are beneficials.
Exactly.
To the growth of of greenhouse products and healthy soil or root microbiome that are really critical, particularly with respect to both pathogen control and optimization for growth. So, there's a whole host of, work around the biology and productivity and plant science and root system analysis and knowledge that is incorporated into this as well. And so I think, there has to be, also, general acceptance by the industry, right? That works in a paradigm unto itself, and with long history of conventional approaches and understandings. They're interested in yield, the quality of their products, getting their products to market, and it's really that's how they do that efficiently, effectively, and sell their products on the market, right?
Right.
But it's
Exactly.
a business. It is a business. That being said, there's a lot of desire to be environmentally responsible, socially and environmentally responsible, and conscious of the considerations with respect to producing products that have been produced sustainably. So, for whatever credential or labeling they may be yield seeking, they would like to be able to talk about their industry in a very positive way through the methodologies and approaches that they're taking. If it's incorporating new management tools and software for real-time monitoring, for example, and
Yes.
that's particularly important. If it's being able to get some real-time data to understand the stability and sustainability of their system, looking at infrastructure deterioration brought about by harsh chemicals, for example, and minimizing that through different approaches. Can they sense and monitor these things in a way in which they can make real-time decisions and effective decisions for change or mitigation?
Right.
And that includes also for ensuring adequate disinfection, if that's a requirement, and the quality of the water across a wide variety of parameters that might be measured for water quality. The other is minimizing water and also reusing water
Yes,
as
exactly.
well. So these are all things that I would think would be important. But I think thinking about the industry is that they want to be seen to be proactive. They're a highly developed industry that has grown technologically and sophisticated in a very sophisticated way. That's
Right.
true for the entire agri-food industry in many ways, whether it's precision agriculture or precision growth in controlled systems, which is really the intentional feature of controlled growth systems, is being
Yeah.
able to be that purposeful and that controlled in the work that you do. But you also want to achieve other goals as well. But part of that is also demonstrating your commitment, as I've indicated, to sustainability and to products that have been grown under conditions that will be highly received by the receptors of the products.
Yeah, I think, I mean, obviously, some of the work that we've, been studying together for a number of years now, understanding the microbiome a little bit better, understanding whether your system is trending towards resilience or risk, right? Like some of those factors are important. And if you're going to use any sanitizer or disinfectant strategy, at least something that works synergistically or isn't necessarily going to undermine a resilient microbiome within those systems, because we know some of the people that we work with, I mean, they're reusing all of their water, right? So it's a closed system. There's a limited amount of wastewater, and it's highly efficient. And obviously, as you're using less water, the risk becomes greater and greater because you have less water to work with. So in that sense as well, it becomes really important, I think, to have that additional visibility and even be able to detect your trends, whether you're moving towards resilience or you're moving towards risk, and what's kind of present within that mixed microbiome, which is significantly, it can vary significantly as well. I think in drinking water then, so maybe if we can apply the same rules or methods to drinking water, how would you see sustainability on the front end of the drinking water systems? Like, how would you see that potentially improving? And we know from some of our experience where we've worked in systems that, and that's actually true in many applications, where often flushing will happen, water is wasted because, we're trying to pollution, dilution, and so on and so forth. So how do you see sustainability progress in that space?
Well, you want to mitigate, you want to reduce the occurrences of those conditions, right? But I
exactly.
think one way of looking at this might be best exemplified in some work we've been doing recently with respect to looking at hot water networks, and which I think exemplify the issue that where engineered water systems operate under diverse chemical physical conditions that can influence disinfection efficiency. If you know, hot water tanks or networks are really systems that employ thermal control, which is energetically costly and ineffective in cooled sections, right? So that's
Yes.
one way of looking at it. And of course, the hot water networks are using also disinfectants as a disinfection strategy, notwithstanding the what hot water networks are also designed to do as well. What is particular about the use of chlorine in a water distribution system, and particularly in a hot water network, is that chlorine degrades rapidly or at elevated temperatures.
Yes.
And in most hot water networks, we tend to turn up the temperatures higher than that are necessary to control microbial growth. It's
Yes.
not only that you want to make hot water for certain applications. We all like to have a nice hot shower, hot bath, but the temperatures in the hot water tanks and the distribution system are much higher, and we adjust that by adding cold water, mixing cold water. But going to the chlorine degrading, hot water networks remain a persistent challenge for controlling pathogens such as Legionella. So that's something to bear in mind. And so you think about that and saying, okay, if at high temperatures are concerned, should there be maybe an alternative that is more thermally resistant and persistent, for example? So we have looked at the stability and efficacy of stabilized peroxide
Yes.
under hot water network relevant conditions in ultra-pure, synthetic, and chloroaminated municipal tap waters. And what we have found is that using the alternative disinfectant, silver stabilized peroxide, that we could demonstrate increased efficiency of the antimicrobial with increase in temperatures, achieving a greater than 2.4 log reduction of
Hmm.
Legionella within 5 minutes at 55 degrees C.
Oh, wow.
And the full biocidal activity remained after 72 hours at 60 degrees C in synthetic tap water, whereas free chlorine lost that antimicrobial activity at 24 hours. And so in municipal waters, both total and free chlorine concentration decayed below recommended thresholds within a 24 to 40-hour period. Now, we've got this, some work that's just been submitted for publication, but I just wanted to share these features of experiments that are undertaken in the laboratory, but
Yes.
clearly indicate that that we can look to reducing the temperature,
Yes. It's
particularly in control of Legionella, which is one of the more significant challenges in hot water distribution systems. And while we don't see the kinds of outbreaks of Legionella that led to the deaths following the Legions Convention in Philadelphia, if I recall correctly, many years ago, though that Legionella is still a very significant concern. Legionella associates with biofilms. They're very dependent on other microorganisms providing certain nutrients that they require, and they persist. And they can persist also in Acanthamoeba, which are protists that are often found in water distribution systems.
exactly.
So how do you effectively control Legionella? Because we still see outbreaks, and there are still high indications of Legionella in distribution systems. And for the most part, they're not problematic, but they are problematic, particularly for those more susceptible to infection. So we
Yes.
think about an aging population, you're thinking about young children, and the occurrence of large exposure to Legionella, it can cause serious, pneumonia-like symptoms
Yeah.
and
Yeah.
infections, and they can be very serious and hard to treat. So it's still a very significant feature and important control. And so, we're challenging this. I mean, this is a well-known problem for a long period of time, but if you start turning the lens to things like sustainability, thinking, well, want to lower the cost of of running a hot water tank and maybe reducing the temperatures, still generating hot water that's needed. Uh, you know that begins to change how you might want to look at the strategy, right?
Yeah. No, absolutely. I
And
mean,
of course, eliminating what might be for the secondary distribution system, more corrosive chemicals, and moving to more sustainable and products that do perform as well or better.
Yeah, no, I agree.
in these particular conditions. And I'm not selling a particular
No, no,
disinfectant.
we
All
agree.
I'm saying is that looking at alternative strategies, though, may be more important. It may mean maybe eliminating chlorine at this secondary disinfection and putting membranes and UV technology at the point of use, right? I mean, you have the options, you have a variety of options, but
You do,
but you
but the
you
problem,
do need the disinfection in the tank. The water sits there and can pool for very long periods of time.
yes,
That's
exactly.
important. You cannot leave it without some
Yeah,
disinfectant.
yeah.
And
SanEcoTec actively, we do Legionella risk assessments, and we've adopted some of the best practices from other jurisdictions where this has become law. And we're kind of hoping at some point that the regulations catch up, obviously, over here as well. But, besides thermal disinfection and regular flushing, and, it's a systems approach again, where you're looking at residuals, and you're monitoring continuously. And in fact, what we've learned as well is that incoming city water is not consistent. It can be quite variable, and in fact, particularly if it's surface water, I mean, seasonality has a significant impact, and we see that the microbial load, even though that water would be safe and compliant from a regulatory perspective, it still brings in variability, as we've been tracking now, hospitals for multiple years, and are seeing, this variability. And we see that has an impact downstream, where, you get to your hot spot, your low flow, no flow area, or your showers, where, suddenly you see a significantly higher signature of microbial load showing up within that distributed system. So all of those things to say that what we see from our digital tools and our data very much corresponds to some of the things that you're saying as well.
so, I mean, I think you reinforced, I think, a very important feature of what we have available today with regards to the tools. So it's not merely just swapping a chemical.
Exactly.
You can really start thinking about a broader and holistic framework for managing water using data, and the power of data is very, very important. And I think that's a significant transformation. And one of the reasons I think migrating to distributed systems across both wastewater and to the water treatment side, and thinking about large, small, and medium size, to how that data can be shared in a way in which helps to inform people on appropriate management parameters. Now, of course, in the case of private operated systems and so forth, where issues around lost productivity, efficiency, yield, quality of product, and a whole host of other considerations are equally important as well. But I really feel the power of data, power of digital technology and artificial intelligence to bear on the tools that can be employed in concert to lead to more effective management
Yeah.
of your
No,
water
absolutely.
systems.
Completely agree. We work a lot with municipal pool clients as well, helping them optimize their pool systems. I don't know if you heard, but today there was in the news a multiple casualty event at a hotel pool in Alberta, with more than 30 children severely affected by overchlorination and disinfection byproducts in the water and in the air. And for our listeners, many jurisdictions actually they've started to consider all health effects in pool chemistry and air quality. But yet, for us here, we still sometimes seem to be stuck in the more is better paradigm from a chlorination perspective. Like, what are your thoughts based on evolving science? I mean, we see this, on a daily basis, that it's possible to be compliant, safe, and effective, if I can use those words. But, this is clearly not a smart approach. And I know that in hotel pools, it's different from municipal pools. There's a lot more controls. But clearly, to me, this is another indicator of where we're not using the most recent or the most evolved science in understanding how to manage a pool system, which is also a distributed system, obviously.
For sure. And so I think it reveals several things to me. One is, the need for education and training at the local level, right? I think,
Yes,
and that managing water systems is complex, even when you're managing under conventional approaches. And
exactly.
we've seen that very value proposition and principle, when compromised, can have horrific effects on water. Just when thinking about just the fundamental basic education, and And that is now important to understand with respect to the kind of knowledge and information is available today that wasn't available a decade or 20 years ago or 30 years ago. We still operate under paradigms that are outdated. Um, you know, pools are complex systems, and their water systems are used quite intensely, and where loads and risk issues are more complex. And from the source water that feeds the pool to managing the pool under the conditions it's being managed, and thinking about the risk to the users or those who are in the pool as well. And
Exactly.
so that bears greater consideration than being that we give to it. I think there's been some benevolence to in the way in which water management occurs, and you just follow step 1 through 10, and you put 2 drops of this in here, 3 drops of that in there. You can check the status of your water or otherwise, but that's not enough these days, right? It's just not enough. It's
And
much
it's
more
not necessary. I mean, if you have a proper control and monitoring apparatus that's actually, that's fully online, that's fully integrated, that actually issues alerts, that gives you early warning before it becomes a problem, then you could avoid, a lot of these problems. So we get back to our original conversation, or where we're talking about the analytical piece in all of this. Like it's not enough to have someone come in and check your hotel pool once a week, right? That's not going to do.
So it's interesting, I've often felt that, we don't value water enough. And it's sad to say we don't charge enough, or we don't price it out in a way which addresses the opportunities, but also the important responsibilities we have to ensure that water is safe. It's the areas that we minimize in some respects, because we seem to rely on existing paradigms and assumptions about how that quality water might be under a set of conditions. And I think we need to take a different view of how we value water and what the investments might be to manage water supplies.
Yeah, I agree. I mean, I don't know what you think about, and rather than just monitoring for minimal compliance, I think it would be really important for us to look more holistically at key performance indicators, not just any biological or microbiological risk, which is important, of course, but also a chemical risk. Like, we should really be looking at these things much more holistically. Like, what do you think?
Well, I think so. And I think one of the revealing features of this is really looking at the emerging science that's revealing, features of that are really only coming to bear on significant public health concerns. So if you look at antimicrobial resistance in water systems, which is a serious and widespread threat to public health, I've
Yes.
written widely and on aspects of water systems being hotspots for emerging antimicrobial resistance, and have done some studies along this line and looking at the occurrence and of antibiotic resistance in wastewater treatment.
Yes.
But it's now, it's recognized that current water treatment processes are not designed for the effective removal of antimicrobial resistance,
Right.
and that water treatment plants are major reservoirs of AMR dissemination. So, a lot of focus has been on the wastewater side,
Yes.
and even there, mitigation is not clear, but certainly a major hotspot for types of biological processes that lead to the amplification of antibiotic resistance and horizontal gene transfer,
Yes.
contributing to AMRs, which are well established, emerging contaminants. We've written on antibiotic resistant bacteria and antibiotic resistance genes in water systems. But for water, it's not clear that that's been mitigated in any way.
Right.
But keeping in mind that chlorine is the most widely used disinfectant for the treatment of drinking water, and has been, as I've said, for over a century. And so we're not. Let's take primary disinfection and set it aside.
Out of it. Yeah, of
We're
course.
talking about the secondary system, and we believe that it is being recognized that it facilitates the spread of antibiotic resistance bacteria. We're talking about use of chlorine and antibiotic resistant genes in water systems, and that we think that there's a long-term application of chlorine has resulted in the selection of chlorine-resistant bacteria. The constant pressure of chlorine in the system sustains that chlorine resistance. We've demonstrated in our lab the ability to produce a chlorine-resistant bacterium. It's not a stable resistance, but with selective pressure, it continues to be persistent. And the interactions with metals and other antibiotics are important elements of research that's being undertaken by others.
Yes.
And to better understand that. So, like I said, antibiotic resistance bacteria and antibiotic resistance genes are considered environmental contaminants of emerging concern. I don't think we really thought about chlorine resistance bacteria or chlorine as environmental contaminants that way.
I know.
We don't use it that way. And so does it warrant it? People will say, well, look at the risk, look at the 100+ years of use, the safety that is associated with this, and the comfort and the risks. But obviously, it's more complex than that now. Well, we have other more significant risks to healthcare and human health and environmental health that we argue that there should be more consideration for these contaminants of emerging concern.
Yes.
And so I think we believe that a distributed system disinfection strategy where multiple alternative disinfection methods beyond primary disinfection are distributed through a water may reduce the impact that chlorine has on antimicrobial resistance and improve microbial control. I think this is the beginning of many more studies that has to be undertaken.
I'm sure.
But I think we have some simple ways to think about that strategy. So if I was thinking about building a secondary system, or if I'm operating a private system or others, I might be thinking seriously about what I can do or what I might employ for containing this.
I agree. I think
we argue that distributed systems may help limit AMR dissemination, enhance water quality by having alternative choices and alternative strategies to manage. But the thing with that is the responsibility to monitor and test and
it is.
And in fact, while some parts of the world have begun to monitor wastewater and water treatment, Canada is not overly
proactive
forward in its testing regime. Although we saw elements of appreciation of more pathogen monitoring in wastewater, as it was the case during COVID, and of course many viruses and other organisms can be monitored, as can be antibiotic resistance and antibiotic resistance genes. And so there is some basis using the various molecular techniques that can be done very quickly and more efficiently and at reduced cost than they could be done 10 years ago or a year ago for that matter. There's value in being able to employ those kinds of tests in a more regular basis, periodically. And I think it will help to demonstrate that using and looking to alternative disinfection strategies combined with testing will lead to better choices and better outcomes for society.
I agree.
I think this is the type of thinking that needs to be considered. The data, and I'm not talking data is coming out of my lab. We're talking about a wide variety of
not just
research that's demonstrating. We've just completed a review article we hope to submit to publication that links some of the things we found, but also bringing in a whole extent body of literature that's now being shared in the scientific literature about these concerns.
Yeah. And, it's interesting, like it would be helpful to have a greater collaboration between the different regulatory frameworks and, for example, a hot tub in this situation, in this pool in Alberta, was a hot tub, I believe, that started to create some of the serious chemical toxins being released from the water into the air. But if you think about it, in the Netherlands, where the regulations are the most strict, I think in Europe, but a hot tub maximum allowable concentration for hot tubs is only 2 parts per million for chlorine, right? So here we have a minimum of 5, and we allow up to 10 parts per million of chlorine, which is, a crazy number. And yet, there are other aspects of management and water treatment that also are requirements, where you would be measuring not only your chlorine level, your pH level, your filtration, but you also are checking for trihalomethanes and other disinfection byproducts, because ultimately those are the things, the bromoforms, the chloroforms, the haloacetic acids, the non-volatiles and the volatiles that are generated in high numbers. Obviously, children interacting. I've been in many hotel pools, and we've done a lot of environmental sampling, and we're going to obviously jointly publish some of this data. But it's really quite astounding what we find. But by regulation, nobody needs to measure those things, and that's the challenge, because we find vast concentrations of disinfection byproducts in pools where, if we were in another part of the world, they would close down all of those pools because they would not be considered safe. Whereas here, we just keep adding chlorine upon chlorine, and we've seen some hot tubs where, the control system isn't there to properly manage it, because it becomes very difficult once you start to adopt such really high numbers of chlorine. And I understand people are trying to keep everybody safe and make sure that, there's no infections that can come from visiting those establishments. But, the problem, of course, is that you're trying to deal with one problem, but you're making actually, other problems much worse as well. And I think that's part of the challenge, and some of the, problem solving that needs to happen based on what you're learning in your research, in your review, what's happening in other parts of the world, so that hopefully, we can come up with a more common sense approach to these things. But data is like the key, I think.
Yeah.
Because if you don't measure anything, you don't know anything.
So listen, I'll go back to our earlier work with looking at the mechanism of action of stabilized peroxide, and we published what has been the only paper to date,
yes,
now fairly well cited, on a chemical that had been used for a century.
exactly,
and we're not, and well, I should say peroxide has been used. So I think there's a lot of understanding of peroxide, but what enhanced peroxide, and through the stabilization through divalent cations such as silver, right? And that and transforming peroxide from the kind of disinfectant that is not stable, but it can be used for all sorts of applications. But now it can be seen as an alternative, and that kind of product's been around for a while. But I think it just speaks to the power of research,
yes,
and the value of bringing science and the evidence to bear on what might be outcomes. And I don't expect that we would create such a shift in paradigm to see elimination of options, but what I think we need is additional options, right?
agreed.
And that's the key, and that the choice, whether it's chlorine or an alternative disinfectant in the secondary treatment, is one that's made intentionally, made with good, made with evidence, made with good data, and actually is designed to achieve what are some of the newer features of the outcomes of technology choices. I mean, the earliest days of water, wastewater treatment were very much predicated on one or two or three, if not four max indicators, right? That was it.
Yeah. No, things have changed for sure
And,
in that way.
As we learn more, we'll look at the what we know of plasticizers and chemical fire retardants, for example,
PFAS,
or PFAS, and that's causing, and the gravitational pull that pulls scientists in all these directions, right? Well, we got to step back and say, okay, well, how do we achieve sustainable outcomes, right?
Yeah. No.
And I think that takes some real power and energy and influence at the regulator level. But I think also scientists have to be stronger advocates, working with private sector companies who are delivering technologies to receptors who are looking for tools to help them do their work better and more sustainably. I think there's a real power of opportunity through this collaborations and these initiatives. And like I said, the power of data comes through bringing real world data, as you've done, to help inform the kind of questions that we might have to ask or should be asking in the laboratory, and intentionally focusing on those questions and getting the kinds of data and outcomes and evidence that supports the decision making that will yield real impact. And if it is the case, to prove the hypothesis wrong, right?
Agreed.
Prove the null hypothesis. I mean, we need to know, but we do need other options, and that's the whole point of this. And we need the suite of tools, and the power of technology now on all fronts enables us to get there.
Yeah. I think that's a brilliant summary and close of our discussion. I can't believe we're already almost to the hour. Is there anything yet to be said for this. I know we'll have you again, Stephen, as we progress some of the interesting collaborations that we're working on. But is there anything else that you'd like to include in our conversation? Otherwise, I think we're gonna close it for today. But anything I've left out?
Well, I mean, we can go on for hours, I suspect.
Very good.
I suspect there may be others out there who will say, he didn't say this and he didn't say that. And but I think this is an ongoing conversation.
It is.
We touched upon a few things further to our initial conversation 26 episodes ago, or whatever the number was.
Yes, indeed.
And we continue to move forward. And I think I'm excited by the industry as a whole, bringing a broader and deeper range of skill sets and science and management tools to the table. And I think that's only going to better the outcomes for more sustainable options. One thing I may add, though, and I think I made references to at the start, I mean, there are digital twins is a really important platform for design. And,
Yes.
If you want to start testing these in a way that gives people comfort, is to think about the modeling through a digital twins framework, right? And to really truly understand the whole life cycle, understand the costs, understand the implications, understand the risks. You can bring the human dimensions, you can bring other features, including the environmental systems, the quality of the water,
Absolutely.
source into the equation. Anyway, I think the power of digital twins can be very helpful to give people confidence in how best to navigate the evidence and the tools, because then they can test the choices and the options out and see what that leads.
Exactly. And that's exactly how we work with, collaborate with clients and stakeholders in this space, because that's the only way. We have to use those digital tools. We have to get that analytical piece in there as well. And then the results will either prove it out or will demonstrate whether it's working or not. I think that's
and it's an interdisciplinary effort, right?
It is.
It's not just bringing the digital and engineering features to the conversation. You're bringing the chemistry, the microbiology,
Everything.
Integrated
approach.
Hydrology. You're bringing a whole range of features.
Exactly.
As well.
Exactly. I think that's a great call out, and I think a good final point. Stephen, thank you as always. Great stuff. I mean, like I say, we could talk for hours, I think, but hopefully for our listeners, you found this useful. It's always exciting me what happens in the research world, in the laboratory, and what we learn from our application, how those two things really kind of meet brilliantly. And that's the application of science, right? So I'm very excited about that. And I'm really appreciative to you as a person, and also all of the work that you've contributed over these years. Thank you so much for joining us today. I really, really enjoyed it. And thank you to our audience for listening. You can re-listen to this episode by subscribing to our YouTube channel, or go to any of the podcast platforms that you like. If you have ideas for future topics or something that Stephen and I haven't touched on, please do email us at mywatertalks@sanecotec.com. Please don't forget to subscribe, share, or like our channel so that you can hear more about exciting future episodes and any interesting updates. Thank you all very much. Stephen, thank you. Have a wonderful rest of your evening, and we'll see each other again soon.